Module 5 review. Number 1 provides us with an equation and asks us to analyze it from the domain all the way down to the asymptotes. So I'm going to go into Desmos, and I already took time to plug it in. Now notice when you do plug it in that it's important you use parentheses. We have the numerator separated by the division sign and then the denominator again in parentheses. Okay, there's also a couple things to remember about this. Now on the bottom, each one of these parentheses, when you set it equal to 0, you get an answers of -4 and of +3. Now watch, again, -4, when I set this parenthesis equal to 0, x equals -4 and x equals +3. Notice that those are the vertical asymptotes. And if we set the top equal to 0, we'd get an answer of -2. Again, watch, we have -2, and that represents the x-intercept. Now, how do we find the y-intercept? We can go right over across, and we can click on it, and it will show us where the y-intercept is. Okay, well, let's start by doing the x and y-intercepts, since I can visually see that one x-intercept, the only x-intercept is here at -2, 0, and I have a y-intercept at 0, and it's approximated, but -0.167. I'm going to come back to the sheet, and remember, if you did not know, if you didn't know how to find the x-intercept by taking the numerator and setting it equal to 0 and solving, you could have just taken the graph and went right over the top, and if you hovered over the top of where that line intersects with the x-axis, it will provide you with the x-intercept. In the same way, I'm going to hover over where this line intersects the y-axis, and I can see the y-intercept. Okay, so now let's talk about the domain. If I move this back, I can see it comes from the far left, keeps coming, and then it goes down as it approaches -4. Okay, jumps over what I'll call this asymptote, it's like a wall, and then it goes from -4 to 3, jumps over, and then goes from 3 to +infinity. How do we write that down? So the domain goes from -infinity to -4, from -4 to +3, and from 3 to +infinity. Remember, these are describing the x values. Now let's look at the y values, the range. There's no limit how far down it goes, and there's no limit how high it goes. For that reason, when we write down the range, it's from -infinity to positive. Where is this function increasing? Remember, increasing and decreasing intervals use x values to describe the areas in which it is increasing and decreasing. Okay, well, let's look at, we have 3 parts. We have the one to the left, the one in the middle, and the one on the right. So we are going to look at this from left to right. From left to right, if we take and we just slide along the line here, from left to right, it is continuously going down. So I know this region is decreasing. From left to right here, if I just grab a point and I continue to go along the line, this entire region is decreasing. And up here, the same thing. From left to right, this entire region is decreasing. So, where is it increasing? There's no increasing intervals. And we just were able to show, this should say not describing, but decreasing. The decreasing, we said every one of the three parts, the left part, the middle part, and the right part, were all decreasing. So when I write down where is it decreasing, I can say it was decreasing from -infinity to -4, from -4 to 3, and from 3 to +infinity. All 3 of those sections were decreasing. Let's go back and just check. So this section, in terms of x values, we can see it's decreasing, it's going down in terms of x values. It comes from the far left, and it continues to go until it approaches -4. This middle section, after we skip over -4, it's going to go from -4, and it's in between -4 and +3. And then after 3, it's going after 3 all the way to +infinity. And that's what this interval notation represents. So I've done domain range, increasing, decreasing in terms of x values. I've identified the x and y intercepts. Let's talk about the horizontal and the vertical asymptotes. Now, if I went up here and I foiled this out, it would look like this. So here's my top, and here's the bottom. So I'm going to multiply the fronts, the outsides, the insides, and the last. And then I'm going to abbreviate this, so it'd be I'm going to simplify this. It would be x plus 2 over x squared plus 1x minus 12. Okay, what I want you to focus on right now is I want you to focus on the degree in the numerator and the degree in the denominator. Degree means what is the highest exponent on the variable. So the exponent on top is a 1 and the exponent on the bottom is a 2. Whenever the exponent or the degree on top is smaller than the degree on the bottom, we say there is a horizontal asymptote of y equals 0. And that's the same thing as the x-axis. And really that's true of both the far ends. So as you go and think of the end behavior, you go to the far left and the far right, you'll see that it approaches that. Let's look at this. So I'm going to go off to the graph here. I know that y equals 0 is a horizontal asymptote because the degree on the top is smaller than the degree on the bottom. I'm going to change the color so it stands out for you. I'm even going to make these dotted because asymptotes are represented with dotted lines. Let's see here if I can do this again. Well, I'm not sure how to change that. So anyways, I can see that here, at this point right here, let's try one more time. Give me one more chance to try this. Okay, so the asymptotes are all dotted lines, right? Because they're invisible. And I can see that for horizontal asymptotes, vertical asymptotes, please listen, vertical asymptotes will never be intersected by the function. So what you see in red, will never, ever, ever cross the vertical asymptotes, which happen to be blue and gray on the screen. Now, horizontal asymptotes are just slightly different. Horizontal asymptotes say that as the function goes to the far left, it's going to get closer and closer and closer to that horizontal asymptote, and I can see that. See how the red is approaching the orange line as I go to the far left, and then when I go to the very far right, this red function, or the function in red, is again approaching that horizontal asymptote. It will never cross it to the far left and the far right. That's what horizontal asymptotes do. In the middle, sometimes, occasionally it will cross. We can see that. And sometimes there's been questions from students that say, I thought you taught us for asymptotes, they never get crossed. There are these invisible walls or lines, and the function never crosses it. Once again, verticals will never be crossed. Horizontals really are going to be described in the far left and the far right, okay? In the middle, it's very possible that sometimes it will touch it or cross it. So in this particular graph, I have a vertical at x equals, because it crosses through the x-axis, x equals -4, and x equals 3. So I'm going to come back here, x equals -4, vertical x equals -4, and x equals 3. Now, how was I able to achieve those if I just simply looked at the graph? Because on the bottom, when you set the bottom equal to 0, we're able to figure out the vertical asymptotes. So whatever makes this 0, -4, whatever makes this 0, +3. And we can't just write -4 and 3. It needs to be x equals -4 and x equals 3. This is the equation of the vertical asymptotes. Again, why do we have a horizontal asymptote? Because the degree on top is smaller than the degree on the bottom. Then for every situation, when that occurs, you'll always have the equation y equals 0. This particular module is working with rational expressions. So they're expressions that contain fractions. Remember, whenever you're adding or subtracting fractions, you need a common denominator. When you're multiplying or dividing, that is not necessary. So much of the remaining problems from this point on are just going to be simplifying. Okay, I need a common denominator. So I'm going to put that on the bottom right away. There's the left and there's the right. Okay, this was on top and this was on top. Now, in order to do this, I need to take this part and I need to multiply it on the left and on the right. So the left and right gets an x minus 1. And the right-hand side gets an x minus 3 and an x minus 3. Now I can see visually that I have an x minus 3 and an x minus 1, an x minus 3 and an x minus 1. Whatever you do to the bottom, you must do it also to the top to preserve the value of this fraction. So I did an x minus 1 here, I must do it on top, and x minus 3, I must do it on top. So the common denominator is x minus 1 and x minus 3. So I already have that down. Now what needs to be attached to the x plus 5? It would be an x minus 1. What needs to be attached to the x plus 2? It would be an x minus 3. And now it's just like it's grunt work and just getting this through. So I'm going to take it down here and I'm going to FOIL this portion. So foiling is front, outside, inside, and last. Then I'm going to put down the plus sign and I'm going to FOIL this portion. Front, outside, inside, and last. If you're confused with foiling at this part, just Google foiling. You'll see quick videos that can pop up and review what to do. Alright, now this is just the numerator. Now I'm going to go, what can I combine? So 1x squared and 1x squared is 2x squared. And I'm going to combine the x's. So negative 1 and 5. Negative 1 and 5 is 4. And negative 3 and 2 is negative 1. Okay, so positive 4 plus negative 1 is positive 3x. Negative 5 and negative 6 is negative 11. This is the numerator. The denominator can remain in parentheses. You don't have to FOIL it. Finally, problem 3. Notice that we do have division. When we have an expression with division, we switch division into multiplying, and we always take the second fraction, we flip it. Not the first, the second fraction, we flip it. Now I'm going to see, can I FOIL any one of these expressions in the numerator, denominator, and so on. So I wrote them all down, and I'm going to try bottoms up. So 1 times 25 is 25. I'm looking for two numbers that multiply to equal positive 25 and combine to give us 10. So two numbers that multiply to give us 25 and combine to give us 10. 5 and 5, and they would both have to be positive. So let's check that. X plus 5 and x plus 5. Multiplies to give you 25, positive, combines to give you 10. Okay, that works. Now I don't have to worry about bottoms up because the leading coefficient is 1. So I'm going to switch this, and in the numerator I'm going to write x plus 5 and x plus 5. Sorry. In the denominator, do I know two things that multiply to give us 9, combine to give us negative 6. So 3 and 3 multiply to give you 9 and positive, but it's not a negative 6. Now if I make them both negative, still multiplies to give us a positive 9 and combines to give us a negative 6. X minus 3 and x minus 3. And because the leading coefficient is 1, I don't have to worry about it. Now I'm going to turn division into multiplying. Okay, looking in the numerator of the second fraction. X squared minus 25 is a difference of squares, so it's x plus 5 and x minus 5. Now this was on top in the numerator. When I change from division to multiplying, the numerator now goes in the denominator. And I'm going to see, can I factor the last trinomial? What multiplies to equal 12 and combines to equal negative 7, negative 3, and negative 4. And just like the other trinomials, because the leading coefficient is a 1, I don't have to worry about a bottoms up. And similar to the last part, this was in the denominator, but it gets switched to the numerator. It gets switched to the numerator when we go from division to multiplying. What do we do with this? Okay, so think of this as one row on top and one row on the bottom. So if there's any x subtract 3's on top, I get to, and remember, they're not just disappearing, really, they are dividing to simplify to equal hidden 1. So for every x minus 3 on top, this quantity, if I see any quantity of x minus 3 on top and on the bottom, they get to be, we think of them as cancel out, but they are reduced to 1. And the x plus 5 and x plus 5, it doesn't matter which one you do, so we're left with x plus 5 times x minus 4 over x minus 3 and x minus 5. That is our simplified answer. Let's look at number 4. 4 is very similar to number 2. Number 4 is very similar to number 2. I need a common denominator. This is one quantity, and here's the other quantity. So again, right away I'm going to write x plus 2 and x minus 1, just like I did last time. I have a 4x on the left, and I subtract 3x minus 2 on the right. Now, in order for me to do it like this, I need to assume that I've already found the common denominator. So x plus 2, so you can visually see this in x plus 2. The left side needs an x minus 1 and an x minus 1. And then I can look, okay, they both have an x minus 1, both the left and right. They both have an x plus 2. Whatever you multiply on bottom, you must also do on top. So with the 4x, I need to attach an x minus 1. And with the 3x minus 2, I need to attach an x plus 2. And now this is just like problem number 2. So I'm going to start by distributing the 4x. 4x squared minus 4x. Okay, bring down the subtraction. Now that subtraction has to last us all the way through. It needs to be able to be distributed. The whole way through, everything to the right of it. So let's go through and with me, we're going to FOIL this. Multiplying the fronts, multiplying the outsides, the insides, and the last. Combining like terms, I have 3x squared plus 4x minus 4. Now I'm going to distribute that negative sign, and all it does is it just changes the signs. It's always in back of it. So negative 3x squared minus 4x plus 4. This is all the numerator that I'm simplifying. Now combining like terms, I have 1x squared minus 8x plus 4. This is not factorable. This is the numerator. The denominator, if I go back to this, was x plus 2 and x minus 1. It is not necessary to FOIL this out. This is the final simplified. Simplifying the expression in number 5. Well, I can see everything in the numerator has an x. Let's pull out an x, and I'd be left with x squared minus 2x minus 15. And I'm only going to work with the numerator first. Then I'm going to try to factor this trinomial. What multiplies to equal negative 15 and combines to equal a negative 2. Okay, here's the x that was left over. That would be a negative 5 and a positive 3. Negative 5, positive 3. Let's make sure. Multiplies and combines. Because the leading coefficient is a 1, I don't have to worry about a bottoms up. This is the numerator. Okay? Denominator. X squared plus 7x plus 12. What multiplies to equal 12 and combines to give you 7. X plus 3 and x plus 4. Okay, so I'm going to write that down. On top I have x. Oops, excuse me, you can't see that. Here we go. On top I have x, x minus 5, and x plus 3. In the denominator I have x plus 3 and x plus 4. Again, since the leading coefficient is just a 1, I don't have to worry about a bottoms up. What can I do here? Because I need to simplify this fully. Well, there's no single x's on the bottom. There's no x minus 5's on the bottom. There is an x plus 3. That means my final answer is x times x minus 5 all over x plus 5. Which of the following is a proper traditional function? So this is not a term that I traditionally use when talking about rational equations, but proper traditional function means that the degree on top, so you have a degree on top and a degree on the bottom. And if those terms seem foreign to you, it's referring to what is the highest exponent on a variable. So this has a degree 1 on top, 1 on the bottom. Degree 2 on top, 2 on the bottom. 2 on top, 1 on the bottom. 1 on top, 2 on the bottom. So I'm looking at the exponent, the highest exponent on a variable on both bottom and top. Now if something is in proper traditional function, the degree on top is smaller than the degree on the bottom. So 1 and 1, okay, that's not going to work. 2 and 2, they're equal, that's not going to work. 2 and 1, okay, not going to work. 1 and 2, so this has a hidden 1 and a 2. The 1, degree on top is a 1, degree on the bottom is a 2, so the top is smaller than the bottom for the degree. This is improper. I come back to 7, but let's talk about 8, because a proper traditional function where the degree on top is smaller than the degree on the bottom is just the opposite of when you have a slant asymptote. So if you're thinking, what the heck is that? So we have vertical asymptotes, and in this video I talked about how the graph will never cross a vertical asymptote. And then we have horizontal asymptotes. And with horizontal asymptotes, we're really focused on the ends, both the far left and the far right. And our function will get closer and closer to this asymptote, but it will never cross it on the far end. And then we have something that's referred to as a slant asymptote. Now, it's the same concept. It's the exact same concept, but it's a slant. So it's a diagonal asymptote. And so we'll have functions. You'll learn about these next year. At this level, we're just talking about when can you expect it. So you may see something like this. Comes up like this and goes like that, right? It's going to get closer and closer to that slant. Now, when can we anticipate that to happen? Well, instead of the degree being smaller on top than on the bottom, it's exact opposite. You probably want to write this in your notes. For a slant asymptote, when you have the degrees and you look at them, it's going to be larger on top and smaller on the bottom. So we can anticipate to have a slant asymptote when it's larger degree on top than the bottom. Let's look at the degrees. 1 and 1. Okay, not slant. 2 and 2, not slant. 2 and 1. Okay, larger on top than on the bottom, slant. Oh, I got to go back here. This is a tricky one. Let me explain why this is tricky. Because first, we can see, is it possible? Is it possible? When you think that possible, you're like, these two stand out to me right away, and I go, oh, slants, right? Larger on top than the bottom, larger on top than the bottom. But first, you need to actually see, is it possible to simplify this first? Like, for instance, x squared minus 4 breaks into x plus 2 and x minus 2. On the bottom, I have x plus 2. So the x plus 2 on top and the x plus 2 on the bottom, they don't just disappear, they simplify into 1, and you're left with x minus 2 on top. So this is the equivalent to just x minus 2 over 1. X minus 2 over 1. Okay, we'll talk about it in a little bit. Let's look at this one. So this is going to factor into, oh, that can't factor. There's no way to factor this. It looks like it's tricky, right? You're thinking 3 and 4, but a positive 3 and a positive 4, although they combine to give you 7, a positive 3 and a positive 4 do not combine to give you negative 12. This is not factorable, so the expression, the degree on top is larger than the degree on the bottom. This is our final answer. So the takeaway is, once you identify what you think could be the slant asymptote, you do have to see, can you first simplify it? Because in simplifying this, I was actually able to eliminate C being the choice, and the only answer is D. Is an extraneous solution to this equation. Extraneous solutions mean that you're going to break a math rule. The most common math rule is you can't have 0 on the bottom. So which one of these could I substitute in for x, and then the denominator would equal 0? So negative 12 plus 3 is not 0. Negative 3 plus 3 is 0. Correct answer. So if we go back here and we talk about where can you define things on a graph, remember that we are able to figure out the horizontal asymptotes go this direction, in a couple ways. Notice how option this is 1, option Roman numeral 1, 2, and 4. See how they are all in a different form than 3? We are able to identify the horizontal asymptote. And actually, I see a mistake in this in what I just created, so I want to change that. Let me change this right now to a negative 3. In this form, the number that's all the way in the back, this is in graphing form, this will be your horizontal asymptote. So y equals negative 3 is the horizontal asymptote. In this form, how can we be able to identify the horizontal asymptote? Well, when the degree on top is the same as the degree on the bottom, like we have in option Roman numeral 1, you take the coefficients and divide them. 5 divided by 5 is 5. Here, when the degree on top is the same as the degree on the bottom, you're going to divide the coefficients. 1 divided by 1. Now, that's not the same form. Let's go down here. So I have the form similar to 1 and 2. When the degrees are the same, 1 divided by 1 is 1. So this would be horizontal asymptote of 5, of 1, and then of negative 3. So if I change that for the next class, then the correct response would be 2 problems left on this review. In problem number 10, there are 5 different parts, and each part gives you a different expression and asks you to simplify it. So how do I combine 2 fractions? Well, I need to have the same common denominator. The x plus 2 And the x minus 2 is different. When I'm adding or subtracting, I need the same common denominator. So x plus 2 and x minus 2. Here's the 5, and here's the positive 4. Now, this side is missing an x minus 2. This side is missing an x plus 2. So to the 5, I'm going to attach an x minus 2. To the 4, I'm going to attach an x plus 2. Then I distribute, and I end up with 5x minus 10 plus 4x plus 8. So when I combine, 5 and 4 is 9, so I have 9x, negative 10, and positive 8 is negative 2. There's my numerator. Here's the denominator. There is no need to go ahead and factor this out. You can write it just like this. Let's look at this. Okay, what multiplies to equal 32 and combines to give it negative 12? That'd be negative 8 and negative 4. Multiplies combines, lead coefficient is 1, so I don't have to do bottoms up. What multiplies to equal negative 24 combines to equal negative 5, negative 8, and positive 3. So when I simplify this, the 8s are going to divide to simplify to 1. I'll be left with x minus 4 over x plus 3. Let's look at the third one. The third one is very similar to the first one. Again, now how do I do this? Immediately I write the denominator of both in the bottom. And then on top, I need to take this one and attach it to the far left, putting in the plus sign, and take what we see in the numerator and attach it to the opposite, which is, again, x plus 2. So again, this gets attached up here, and this gets attached up here. Okay, I'm going to go through and I'm going to FOIL this. X squared minus 3x minus 1x plus 3. And I'm going to FOIL the back. X squared plus 2x plus 2x plus 4. Now I'm going to combine like terms. 1x squared and 1x squared is 2x squared. Okay, negative 3 and negative 1 is negative 4x, and 2 and 2 is a positive 4x. Well, negative 4x and a positive 4x, they just cancel out. And 3 plus 4 is 7. There is, excuse me, that's a plus sign. There's the numerator, and the denominator as x plus 2 and x minus 3. Let's look at the fourth option. So it's division. Well, remember with division, we don't have to have a common denominator. We're going to turn division into multiplying. And the second fraction, we're going to flip it. We're going to take its reciprocal. Okay, so there's not an x minus 1 quantity in the bottom, but there is an x plus 2. These divide to equal 1, and I'm left with x minus 1 over x minus 3. Now, a really common mistake is students want to continue to try to simplify, and they want to cross out the x's, and then they get negative 1 over negative 3. Can't do that. This x goes with x minus 3, and this x goes with x minus 1. That's in full simplified form. Down here, I'm going to take out a 5, and I'm left with x minus 2. On the bottom, what multiplies to equal positive 6 and combines to give you a negative 5, x minus 2 and x minus 3. Again, they simplify it to equal 1, and I have 5 over x minus 3. Okay, one problem remaining. We want to take the 3 functions and match them to each one of the graphs below. Now, one way that I'm not going to probably choose to do, but you definitely could do, is you could plug this into decimals. This would guarantee you're going to get it right. Plug this into decimals and find out which graph does it look like. Plug this into decimals, which graph does it look like. You'll only have one remaining right. You match it up. I'm going to do it a little bit differently. So here's what I notice. I know that the vertical asymptote can be found on the bottom. So x equals negative 2 is a vertical asymptote. I know in this form, when the degrees are the same, I'm going to divide the leading coefficients. So that tells me the horizontal asymptote is at 1. And I know that x minus 4, whatever's on top, when I set it equal to 0 and I solve, that is going to be the x-intercept. So let's find, out of the 3 choices, which one has an x-intercept at negative 2? Oh, maybe down here. So at negative 2, that's what this is. Okay, that's right. It has a y-intercept at 1. That's exactly what we looked at. And it has an x, excuse me, I may have said the wrong terminology. It has a vertical asymptote at x equals -2. It has a horizontal, I'm getting tired, a horizontal asymptote at y equals 1, and then it has the x-intercept at 4. So C belongs to option 3. Okay, let's look at the next one. So I look right here and I go, is it possible that I can factor this? Well, let's see, what multiplies to equal -5 and combines to give you 4? X plus 5 and x minus 1, x minus 1. Well, they're going to cancel, and I'm left with simply y equals x plus 5. Well, how do I graph that? Well, I start at 5, and then the slope is 1 over 1. So start at 5, 1 over 1. A goes with option 1, and then the remaining one goes with option B. The remaining one goes with option B. And again, if you didn't like that method, you could simply plug them into decimals and identify the correct options.